Hello, my name is Andrew McPherson, and I am presenting on the development and potential benefits of a motor-augmented wrist-driven orthosis, or MWDO, to improve tenodesis grasping for individuals with C6 and C7 spinal cord injuries. By having two simultaneous modes of actuation, a spectrum of grasping behaviors can be explored. There are nearly 300,000 people currently living with spinal cord injuries in the US alone. Restoring hand and arm function is reported to be the top priority for people with tetraplegia given the associated loss of independence. This device is designed for C6 and 7 cervical level spinal cord injuries corresponding to those who retained wrist extension with minimal to no voluntary wrist flexion or finger movement. These individuals often learn to use new ways of grasping, such as tenodesis. Tenodesis allows individuals without voluntary finger movement to perform prehensive grasping through the passive coupling of wrist extension and finger flexion. This grasp depends on tightness in the fingers and flexor tendons to pull the digits closed from wrist extension, as this video demonstrates. However, tenodesis only provides very limited grasping and thus limited functionality, as the fingers are easily forced open. Passive wrist-driven orthoses, pictured in A and B, seek to provide a simple solution to increase the effectiveness of this tenodesis grasp using a 4-bar linkage, as the video demonstrates. The 4-bar linkage amplifies the finger movement based on the wrist extension, while no longer depending on the tightness of the flexor tendons to provide a firm grip. A drawback to these traditional devices for individuals who use a wheelchair is they must contort their arms and trunk at times in order to perform a grasp. Our motor-augmented WDO extends this functionality by adding a secondary actuation method to thus selectively decouple the wrist and finger motion. The motor-augmented wrist-driven orthosis uses an under-actuated linkage design consisting of two 4-bar linkages in series. The point W is located along the axis of the wrist's center of rotation, while M and D are located near the MCP and DIP joints respectively. Point D is constrained by a magnetic hardstop shown in green and provides a preload force such that the distal 4-bar linkage remains rigid in free motion. However, if a force is applied, pictured here as a brown object, the preload may be overcome and the whole hand will wrap around the object. The device is actuated by two inputs, alpha, defined as the angle of the wrist in extension, and gamma, defined as the actuated angle of the motor. The hand can be opened or closed by motor actuation alone, wrist motion alone, or a simultaneous combination of both. The angle between the links actuated by the wrist and motor, beta, correspond to how open the hand is at a given time. A range of grasping behaviors are enabled by allowing for both passive tenodesis grasping from the wrist in red and motor actuation in blue. The angle beta dictates the degree to which the fingers are open or closed on the vertical axis, while the horizontal axis shows how the gain provided by the motor, equal to the change in motor angle over the change in wrist angle, increases from left to right. The device can produce a continuum of grasping behaviors between pure passive and pure motor actuation, which allows for experimentation with hybrid control schemes. The behaviors described were achieved with the current prototype primarily made of aluminum and 3D printed parts. The size and initial prototype is inspired by the open source, fully passive WDO presented earlier from the University of Washington. A rotary, thin-film potentiometer made by spectra symbols is used for measuring the wrist angle alpha located at the wrist joint W. A 12-volt brushed DC motor, an encoder for measuring gamma, is located at the forearm. Motor actuation is transmitted through the bevel gear with limited range of engagement to avoid injury. A wire tether connects to the control box. The current implementation positions the toggle switch and momentary buttons far apart for ease of use by people with limited dexterity due to SCI. The magnets at the BIP joint align the finger linkages until linkage MD movement is inhibited, which initiates a wrap grasp. The first video on the left demonstrates the passive wrist-driven orthosis function. The second video on the right demonstrates the manual button control. As you can see, the bevel gear is actuating the fingers open and closed. With 2 degrees of freedom, the MWDO has the potential to enable a flexible set of behaviors. In this initial work, we demonstrate 3 particular examples outlined in the state transition diagram. Passive state is when the motor stays at a fixed position and the device works like a traditional WDO. Active augment state yields a larger relative grasp motion of the fingers from a small extension of the wrist. Active maintain state is when grasp beta is maintained regardless of the changes in wrist position alpha. For this, the motor tracks the motion of the wrist using the potentiometer. The operator can switch between these 2 active modes with a toggle switch. Both active states are implemented by using position feedback control, using a simple PI control scheme. In either state, the operator can use momentary push buttons to manually change gamma. This is particularly useful in confined spaces or to assist users with C6 SCI to open their hands, given passive WDOs and tenodesis depend on gravity to open the hand when the user is unable to flex their wrist. The push button may also be used to open the hands to grasp larger objects than the user could otherwise manipulate. Here, an author demonstrates a few common activities with the augment mode to grip a set of keys, a pen, and a round doorknob without using finger strength. And here, the author demonstrates the maintain mode by holding a steady grasp on a cylindrical test object without using their fingers and repeatedly extended and flexed their wrist. The controller produces a constant angle between motor and wrist position, which allows the user to maintain their grasp on the object despite wrist position. With a traditional WDO, the object would have been unintentionally dropped as the wrist moved in flexion. This behavior may enable the execution of more complex bilateral grasping and manipulation tasks. This presentation introduces an initial demonstration of the motor-augmented wrist-driven orthosis as a method to enable more flexible operation for functional grasp. However, this is only the very preliminary exploration and requires more evaluation. Future work will involve user testing of subjects with C6 and 7 spinal cord injuries to determine the MWDO's efficacy relative to the traditional WDO. We have assumed that wrist extension is an intuitive way to command grasping for these subjects, but this is yet to be proven. The performance of this device may also be improved by including a break at the wrist joint to increase maximum grasp force, not limited by the user's wrist strength to oppose the motor actuation. Eventually, this device could enable studies in the home to explore the benefits of this device in daily use. In particular, we will address how people switch between operation modes, for example, through gesture recognition. Thank you.